This is Seungjae from NLCS Jeju, and I would like to give a brief introduction about number theory. So, number theory is a branch of pure mathematics that studies about integers and integer-valued function. And this is one of the four major branches of Olympiad mathematics, which are algebra, geometry, combinatorics, and number theory. School topics that's related to number theory and you're familiar with will be stuff like prime numbers, factorizations, division and remainders, and etc. So let's move on to congruent equation. Congruent equation is sort of a language for number theory in which its basic form is A is congruent to B in modulo n. So by definition, it is equivalent to A minus B being some sort of multiple of n. And it looks quite complex, but basically it's just saying that A and B have same remainder when divided by n. So for example, 25 and 13 are congruent in modulus 6 because they have same remainder of 1 when divided by 6. And 3m minus 2 and m are congruent in modulo m minus 1 because if they subtract m from 3m minus 2, it's 2m minus 2, which is a multiple of m minus 1. And these are the characteristics that can be applied to any congruent equation. So if A and B are congruent in modulo n, and C and D are also congruent in modulo n, if we add or subtract, so A plus C and B plus D should be also congruent in modulo n, and also for minus. Multiplication, if A and B are congruent in modulo n, A times K and B times K should be also congruent in modulo n. And division, and there are some restriction when we divide numbers. So given that K can be divided, A and B can be divided by K, and greatest common divisor of K and N is 1, which means that they are co-prime. If A and B are congruent in modulo n, and then if we divide both sides by K, it's also congruent in modulo n. And there are some basic definitions that we have to cover before discussing about these stuffs that will be followed. Complete residual system is a set of numbers in which there's no pair of elements that satisfies AI. Aj is congruent in modulo n. So there are n number of elements in total for modulo n. In other words, it's a complete set of remainders in modulo n. So let's take easy example. In modulo 3, 0 and 1 and 2 forms a complete residual system in modulo 3 because there's no pair of elements that satisfies AI is congruent to Aj, and there are 3 number of elements in total. So we can say that this is a complete residual system for modulo 3. And there can be different forms of complete residual system for same modulo. So if we just keep on saying about modulo 3, minus 1, 0, and 1 can be considered as complete residual system of modulo 3. And the following example, which seems ridiculous, but this can also be said to be a complete residual system of modulo 3 because all 3 are not congruent to each other in modulo 3, and there are 3 elements in total. And then this is reduced residual system. So it's saying that there's no pair of elements that satisfies AI as congruent to Aj in modulo n. But in this time, there is restriction that every element should be co-prime with n. For example, 1, 3, 5, 7 is a reduced residual system of 8 because we removed 0, 2, 4, 6 from the complete residual system because they are not co-prime with n, which is 8 here. And then the next example is 1, 5, 7, 11 will be a reduced residual system of 12 because they are the only 4 numbers that are co-prime with 12. So basically, this is a subset of complete residual system. And to move on, let's cover about some basic theorems in number theory. So first one that I'll talk about is Wilson's theorem. This states that p minus 1 factorial is congruent to minus 1 in modulo p for every prime number p. For example, 6 factorial, which is 720, is congruent to minus 1 in modulo 7. And then 10 factorial, which is 3,628,800, is congruent to minus 1 in modulus 11. And this is true when you calculate, and this can be applied to any prime number that you can think of. So let's move on to proof for Wilson's theorem. And then let's make a congruent equation. M squared is congruent to 1 in modulus p. And that should have at most 2 solutions in a reduced residue system of a prime number p, because it's a quadratic congruent equation. And obviously we can see that the 2 solutions are plus minus 1, because 1 squared is 1 and minus 1 squared is 1. So we already know what the 2 solutions will be. So let's divide it into 2 cases. First case is that the 2 solutions for m squared is congruent to 1 are equal, which means that p is 2, obviously. So it's easy to prove for only 2 because 1 factorial is 1, and we can easily see that it's congruent to minus 1 in modulus 2. So it's done here. And then let's move on to the other cases, the general cases, where the 2 solutions of m squared is congruent to 1 are different, which means that p is not 2. So let's define a new symbol which represents the inverse for multiplication and congruent equation, which means that if we have a inverse of a, which will be represented by a prime, it's shown that a times a prime should be 1 in modulus n. For example, 3 prime will be 2 in modulus 5 because 3 times 2 is 6, which is congruent to 1 in modulus n. So we can, from 1 to p minus 1, we can pair up the elements with its inverse. Unless an element have itself as their inverse, they will uniquely form a pair. For example, if we have p equals 5, well, 2 and 3 will form their inverse pair, and then 1 will have itself as the inverse, and 4 also will have itself as the inverse. And then if we multiply from 1 to p minus 1, every pairs will multiply to be congruent to 1, and only 1 and p minus 1 will remain. So this is the equation that I showed to visualize what I've said. So basically, if we pair up all these inverses of each other, then they will all be congruent to 1. So we can get rid of them, and only 2 that remains are 1 and p minus 1. So that p minus 1 is congruent to minus 1 at the end. And then this is Euler's theorem, which states that a to the Euler pi function n is congruent to 1 in modulus n for any natural number n. That odd-looking pi n is Euler pi function, which represents the number of elements in reduced residue system of n. So if we take back the example from n equals 8, it will be 4 because there are only 4 elements, 1, 3, 5, 7 in the reduced residue system of modulo 8. So proof of Euler's theorem is the following. Let's define one reduced residue system of n as k1 to k pi n. And let's multiply integer a that is co-prime with n to all the elements to get ak1, ak2, ak pi n. And let's note that by definition, any ki is not congruent to kj in modulus n, because it's the definition of reduced residue system. And then if we multiply a to the both sides, we can see that aki and akj cannot be congruent in modulus n for any cases, which shows that AK1, AK2 to AK pi n is also an example of reduced residue system in modulo n. So because they are both reduced residue system of same modulo, K1, K2 to K pi n and AK1, AK2, AK pi n are fundamentally congruent to each other in modulo n. So they are just a rearrangement of each other, which will be something like 1, 2, 3, 4, and 2, 4, 6, 8, where 1 and 6 pair up, 2 and 2 pair up, 3 and 8 pair up, and 4 and 4 pair up. So the products of each set should be congruent in modulo n because they are basically congruent to each other. So let's, on the left-hand side, we have the product of all elements of the first set we have discussed. And then on the right-hand side, there are elements of the second reduced residue system. So if we take out all the A on the right-hand side, we can see that it's the notation is a little bit wrong, but it's shown that A to the pi n to the power of A to the power of pi n times K1, K2 to K pi n is congruent to K1, K2, K pi n in modulo n. And by the characteristics discussed before, we can divide a number that is co-prime to n. And because they are reduced residue system, we can know that all the elements are co-prime. So we can just get rid of K1, K2 to K pi n on both sides. So we are left with 1 is congruent to A to the pi n in modulo n, which is the statement we were trying to prove. And then lastly, it's Fermat's little theorem. Fermat had many theorems that he have discovered, and this is the one which is named as Fermat's little theorem. And this states that A to the P is congruent to A in modulus P. In other words, A to the P minus 1 is congruent to 1 in modulus P. So for example, if we take any number A, like 2020 to the power of 10, then it will be congruent to 1 in modulus 11 because we are taking power of P minus 1. Proof can be simply done by using prime number P for n in Euler's theorem. So we're using P instead of n. So we are talking about modulus P. And Euler pi function, which is the number of elements in complete reduced residue system of n, it will be just P minus 1 because only 0 is not co-prime with P. So 1 to P minus 1 are all co-prime. So we have P minus 1 elements. So if we just insert P minus 1 instead of pi P, then we get A to the pi P minus 1 is congruent to 1. So that's the end of the proof. And this is the basic introduction of the number theory and discussing about some theorems and its proof. And thank you for listening.